Hi, everybody. First of all, thank you to the organizers for the invitation. Today, I'm going to talk about some of the work that we have started doing around 2020. So it was really the pandemia when we started this. We think that there are interesting opportunities in using symbolic numeric computing in computation, in a combination with upscaling theories to actually try to push the boundaries of multiscale modeling for complex systems such as batteries. Now, I'm going to say a dirty word in this audience, maybe, like I'm a continuum mechanics person. Yeah. So my apologies, but essentially the smallest scale that I'm going to be talking about starts from the pore-scale, like Navier-Stokes. So I probably will have to clarify a little bit of jargon, because when I mean finer scale or smaller scale, this is really the scale, the scale that we consider as a benchmark. And of course, I would love to get the correct equations and boundary conditions from DFT simulations at some point. So, let's hope to get there, sooner or later. But despite I will be talking about, again, scales that are dramatically larger than the ones that we have been looking at so far. Actually, I'm closer to Salvatore's type of scales, that kind of porous media structure. Really what we look at is at the impact of dynamics and its interplay with the structure of a porous medium at the system scale, right? So we perform that coarse-graining going from the pore scale and try to approach the device scale. Now, despite the scales are very different, a lot of the conversations that actually have happened really resonated with me also, like on this side of the community, we really talk about, model accuracy, when do we need to use certain models versus others. What we do in our group is actually try to break models, okay? So we are really interested in when models don't work, but we do it with a positive attitude. The idea is that if we know when they don't work, then we know what we need to improve and possibly, understand new physics that we have not incorporated. So we go, to that point from that angle. Now, this is why we are particularly fixated with Karl Popper and the concept of scientific falsifiability. Really, everything we do, we try to do, tries to follow a deductive empirical falsification approach over a more inductive concept of verifiability. Again, we don't try to verify models, but we try to understand when they break. And the reason why, I personally like this approach is that this is described quite well in this writing from Popper. He writes that if we are uncritical, we shall always find what we want. We shall look for and find confirmations, and we shall look away from and not see whatever might be dangerous to our pet theories. In this way, it is only too easy to obtain what appears to be overwhelming evidence in favor of a theory, which, if approached critically, would have been refuted. In order to make the method of selection by elimination work, and to ensure that only the fittest theories survive, the struggle for life must be made severe for them. Yeah, we are going to talk about when theories fail. Now, because I kind of feel a little bit of an outsider, and again, I'm not in the catalysis community, I thought that I would at least, mention briefly what we are interested in our group. We really look at multi-scale, multi-physics systems, and we look at the number of different applications. The common element among all these different applications is that they contain porous media, okay? And so we looked at porous media in geologic context, so we look at rocks. We look at porous media inside batteries, so we look at, again, some electrochemistry, again, and also thermal runaway, which is what I'm going to talk about today. And then we also have looked or are looking at actually thermal protection system for re-entry vehicles that also contain porous media. And we are interested in multi-physics and multi-scale systems, well, because they are kind of hard in general, so they're fun to deal with, and they are in a number of different applications, both in engineering and environmental systems that are critical to sustainability. So this is something we are interested in. Again, just some jargon, although I'm sure that there is quite a bit of overlap here. So when I talk about multiphysics, I refer to a system where multiple types of physics occur concurrently. So it could be advection, diffusion, reaction, heat transfer, electromigration, whatever you can think of. I refer to a system as multiscale when all these different types of physics occur in complex heterogeneous environments that exhibit a hierarchy of scales. One such example is precisely porous media. Why do we say that they exhibit a hierarchy of scale? Because the pore size may be on the sub-micron or sometimes nanometer length scale, but this porous media is part of a device that is much, much larger in size. And ultimately, what we would like to understand is how the structure and the dynamics inside this porous medium really can control the performance at the device length scale. And that's really what goes to the coupling, right? We know that whatever happens at the microscale really can control the performance at the larger scale. So on top of that, we can have very complex reaction networks. In this particular case, I'm just put here some geochemical reactions, but of course, we have seen a lot of super complex reactions in catalysis. So you can think of that beside all these transport phenomena, we may also have very complex reactions on top of it. So how do we approach this problem of handling or translating scales from the pore to, let's say, a continuum? Well, we have at least a couple of approaches or way of thinking about it. We can, again, in this particular case, I'm just thinking about a very basic problem. It's a flow, carries a solute that reacts at the solid-liquid interface with the grains, okay? And this reaction is described by this boundary condition and can be nonlinear, can do all kinds of different things. So one way to model this type of system is that we can, of course, use pore-scale models. If we have a flow, we can use Stokes, or Navier-Stokes equations, depending on the Reynolds number. And then for, to model the transport and reaction, we can use an advection diffusion equation with appropriate boundary conditions on the solid-liquid interface. The other approach is to model exactly the same physics at a different scale. So we refer to continuum scale model or also upscaled models, macroscopic models that are very homogenized models. These are all kind of equivalent type of jargon in our community, means that now we don't distinguish anymore between the pore space, essentially, and the solid phase, but we treat everything as an homogeneous continuum to which we attach effective properties. And so in that context, the way we would represent exactly the same physics is that we would use, let's say, Darcy's law to model, momentum, and we would use an advection reaction dispersion equation to model, mass and reactive transport. Now, what are the fundamental differences? And again, I know actually that in the audience there are a lot of people who do this a lot. So there are a few. The first one is that not necessarily the equations at the continuum scale have the same structure as the equations at the pore scale. Okay, they can be different. That's the first one. The second is that continuum scale equations, solve for spatially average quantities differently from pore-scale equations. Here we would be calculating point-wise velocity and pressure and concentration inside, let's say, the liquid phase that fills out this pore, while at the continuum scale we are solving for the spatially averaged quantity. And then the other part is that at the continuum scale we have effective parameters, okay? So these effective parameters, they emerge as a result of the scale translation procedure. For example, we have the concept of permeability that Salvatore was talking about. This is, again, permeability is a concept that is associated with a continuum, so a transition to a continuum. We have the effective dispersion coefficient. We have porosity, which, of course, is a concept associated with continuum. And I'm sure you know exactly what's good and bad of each approach. approach. Again, we have heard it before for DFT and more other and simplified models, and really the same arguments apply when we scale translate at these scales. We know that pore-scale models, again, I know that somebody will cringe by saying this, but again, I remind you that for us, the truth is the Navier-Stokes equation. So, if we want to, reframe this in a way that is probably more acceptable, we can say that pore-scale models are more theoretically robust, okay? They are based on principles that have a little bit more solid foundations, okay? So that's a good thing, but of course, we need to know the pore-scale geometry everywhere in order to be able to solve them. And if you want to solve the equations over the entire device, of course, this would become computationally unfeasible. Continuum scale models have the opposite advantage. We do not require to know the pore-scale geometry everywhere in the porous medium, but we only need to know the distribution of these effective parameters. For this reason, we can model pretty large systems with a relatively low computational burden, because now we don't have to solve the intricacies of the topology. But this is a big problem. They do rely on simplifications and assumptions. It is wise in general to ascertain before using a continuum scale models whether these assumptions are actually valid. The moment in which we start using continuum scale models, when the hypotheses upon they are based upon are invalid, we lose predictivity. So we have no control on performance, okay? And so a lot of our work is really focused on kind of finding when these models break, so that then we can safely use them and maintain predictivity and be we don't like surprises. That's the idea. Okay, so actually I did not add this now. It was yesterday there, so so I think it's not, I don't see. But anyway, so how do we choose a model? Again, it was mentioned before that, everything should be made as simple as possible, but so simpler, which means that essentially there is always a trade-off. We want to simplify the system, but still retain the physics that is interesting to us. Now, what we do in our group is really essentially to focus on this multi-scale modeling developing framework, where we have a branch where we do physics-based model development, and we do it rigorously. Again, our smallest scale essentially is the pore, and we do this sequentially. Together with the development of models at different scales, we also derive the applicability conditions of that specific model, which sometimes we call, again, applicability conditions or diagnosis criteria. So that every model we develop has also a set of applicability conditions that I will discuss how to get. And then once we have this pair, then we can do physics-based model deployment, which is optimal, right? And this optimal means that the trade-off is probably between accuracy of the model and computational cost. Now, so when we think in terms of the features that we would like our models to have, is that we want control accuracy. So we would like to have a priori error estimates of the error that we expect in this model. And I want to relate a little bit what was mentioned before in the discussion about what defines whether a model is good or not good. I think there has to be a metric to decide that, right? And it seems that the community seems to agree that certain models sometimes work and sometimes do not work. But what for me was missing was what makes you decide whether it's good enough, right? In this particular talk, I have a very, very narrow way of defining a model that works, and it's quantitative. So the way we define it is the model works if the error that is associated with the model actually is bounded the upscaling error that is predicted by the theory. So that's my definition, okay? But of course, in every field, it can be different. So that's my cutoff of truth, right? So then we would like to have realistic complexity, and we would like also to have computational efficiency. At the same time, because we work on different kind of applications, we would like to be able to develop these models really fast, so not spend like decades to kind of come around with a model. And we would like to be able to have a framework that is transferable and general. And again, in this talk, I'm going to be bouncing back and forth for different examples between coarse-graining, between two different scales. So I will sometime refer to the pore-scale versus the continuum scale, which represents this gap in scale translation. And for the application to thermal runaway, I'm actually going to go really big, from the cell scale to essentially the vehicle scale. So, we recently, around 2020, we started working on thermal runaway. This is an important problem. We know it's not good to have thermal runaway. There are a lot of safety risks, associated with it. And so we do strongly believe that accurate predictive models can be used for computer-aided design. And therefore, that the more accurate the model is, the better actually you can then do optimization. And so, again, the issue with this is that it's always the same, it's the curse of dimensionality. We know that this is a Tesla battery pack. It contains about 7,000 battery cells. For each module, you have about 450 batteries, and then this is the structure that you would see. So the white part is a packing material, this is the battery cell, and then this is just a conceptualization of the cooling pipes. And so, again, the idea is that, okay, is there a way that we can kind of think of developing models that can optimize the topology, maybe to prevent thermal runaway or reduce the usage of cooling pipes by, properly arranging the structure of these cells. And so how would we do this? Again, we can use fine-scale models. We know they're accurate, but they are computationally expensive. Or we could use this equivalent continuum approach. Now, I would like to note that compared to the previous case, in this case, we have two overlapping continua, one that represents the battery domain, the battery cell domain, and the white one that represents the packing domain. And these two continua essentially communicate with each other. Now, again, the deal is always the same. There is no free lunch. So we get a computationally cheap approach, but the problem is that we know that there are hidden approximations when we switch to this representation. Now, if we have the equations at the pore-scale, which in this particular case, I will just assume the simplest, absolutely simplest sets of equations. So I'm going to consider that, if there is thermal runaway, this happens just by conduction. Not true, because there are a lot of other problems. There is flame production of oxygen gas, flame propagation, ignition, flame propagation, and so on and so forth. But for the sake of the demonstration purposes, let's just consider that we know the equations, and these are standard conduction equations. Now, the problem generally when you cross scales is that you don't know what the equations will be at the continuum scale. So the whole business here is really calculate this, the question mark. So how do we do this? With controlled accuracy. So luckily, we don't have to invent anything new here, because there are mathematical theories that actually just do that. These are called upscaling methods. What upscaling methods do is that they generate mathematical models for the evolution of upscaled quantities. And that's generally the reason why they're known and used depending on the community. But they actually also allow you to calculate the applicability conditions of the model you develop. That second part, not much talked about, although we think it's quite critical. So what's the basic, I'm not going to go into the mathematics of it, but what's the basic concept of this upscaling method? It's actually quite intuitive. So you you identify what's called generally a representative elementary volume. This is essentially a volume over which you will define your average. Then you define your average. So for example, you can think that this variable psi is temperature, let's assume. Now, the general goal of any upscaling method is to start from a partial differential equation that governs your for example, your temperature. And this can be any operator. I just put here, something, an advective operator, doesn't matter. But this is a partial differential equation that governs the evolution of your pore-scale variable. And the objective is to take an average of this PD, and then behind this arrow there is a lot, write essentially a partial differential equation for the average of your quantity, of your dependent variable. So that's the entire deal. Once we have this partial differential equation that now tells you what is the spatial temporal distribution of the average temperature in this domain, then you can solve it, and then of course you can solve a domain that is much larger than this at a fraction of the computational cost. What are some of the upscaling methods? Again, this is not even an exhaustive list, but some of the standard ones are volume averaging, homogenization theory, thermodynamically constrained averaging, there is CTRW, there are a lot of stochastic approaches. Anyway, there is, again, a very, very rich machinery that allows you to do this. We primarily use homogenization theory, and I'm going to provide a crash course on homogenization theory for those of you who have not seen it before. So what does homogenization theory do? So you start, let's say, with your porous medium. The first assumptions that you make is that you can conceptualize this porous medium as a periodic structure. A periodic structure of a size L, this is the macroscopic size, okay? And then this is characterized, can be built as the juxtaposition of periodic unit cells. Now, the size of this unit cell is small l, and the ratio between small l and big L is epsilon. This is called separation of scale parameter and must be much, much smaller than 1. So what homogenization does effectively is the same effect as looking at this picture as squinting your eyes, right? So if you squint your eyes, essentially you won't be able to see these things anymore. You will see just a homogeneous, possibly gray continuum, and that's the limit where we're going to work on. Now, the theory starts by taking in the pore-scale equation, so whatever physics you want to solve at the pore-scale, mathematical derivation, skip, we get the continuum scale equation. Then now, but we can go into the details if you're interested. But yeah, so we get the continuum scale equations that now govern the evolution of the average psi, where the average is defined over these units, over this unit cell. And then what we see is that we have effective parameters, right? This V, D, and so on and so forth. One thing I want to point out is that these effective parameters generally can be written in terms of a closure variable, okay? This weird chi, okay? So the closure variable is itself satisfies a boundary value problem over here that must be solved just locally once on the unit cell. So if you put everything together, and if you were to, after you do the math, you were to implement this numerically, how would that look like? So you do the math, you obtain the continuum scale equation, you obtain the effective parameters, you obtain the closure problem. So numerically, what you would do is that you start by solving the closure problem for the closure variable chi on this unit cell. Once you know the closure variable, you plug it in and you calculate the effective parameters, then you can plug into your continuum scale equation, and then you can solve at your macroscopic, in your domain. Now, the importance of the closure variable is that it is in this closure variable that all the information about the topology of the structure comes into play into your continuum scale model. Okay? That's that. So as of now, I told you essentially how generally you get the continuum scale equations and the effective coefficients and how disclosure variables plays a critical role. But I didn't tell you something quite important, which is what I talked about a lot before, which is these applicability conditions. How are we going to find these applicability conditions in this procedure? For this, I'm going to just use a typical, like, spherical cow kind of problem, just to make a point. So where do these applicability conditions come from? So let's consider a very, very simple, it's the simplest scenarios possible. This is essentially a channel where we have a flow and we have a solute that is being carried with the flow. The solute, so this is an infinitely long channel, so we know what the velocity field is, it's a parabolic. And then this solute C is advected and diffuses, but it can also react with the top and bottom walls according to this very simple linear reaction, okay? So if we were to construct an equivalent or continuum representation of this system, first step is to define the average. In this case, an average, a very intuitive way to define the average is just to define the average along the vertical cross-section over here. So if you apply this operator to these equations, and you can find a lot of long derivations in this paper, which is not by me, but by a French mathematician, you will eventually get to this continuum scale model. Now, these continuum scale models have kind of all the features that we expect. This is, an equation, an advection, a reaction dispersion equation that is valid, is satisfied by the average concentration, and it has effective parameters, is one-dimensionally spaced, of course, because we have averaged out the vertical direction. But what I would like to point you out is actually the effective parameters. For example, this effective reactivity, K, big K. Now, of course, effective reactivity must be related to the reactivity at the pore scale, this curly K, which it is. And it also depends on this Damn-Collar number, which is defined here. So the way in this particular case, Damn-Collar number is defined as the ratio between the diffusive time scale and the reactive time scale. So intuitively, if Damn-Collar number is much smaller than 1, it means that the diffusive time scale is much smaller than the reactive time scale, which means the diffusion is faster, okay? So let's now, for the sake of argument, consider a situation where, when for whatever reason, the reactivity of this wall increases. So K increases, okay? And so if K increases, what we see is that, again, the physics has not changed. We are just literally making this wall more reactive. What we see is that as K increases, also Damn-Collar number increases. But what happens is that when Damn-Collar number becomes greater than 3, then the effective reaction rate changes sign, which of course is unphysical because we haven't changed whether this is an absorbing or desorbing boundary. We have just made it more reactive. So where is the problem? Well, the problem is that, again, this continuum scale model is not supposed to work always. There are applicability conditions that are intrinsically related to the dynamics of the system. So this continuum scale model is a perfectly legitimate, accurate model when Damn-Collar number is smaller than 3. And after that, well, you can use it, but then don't blame the model for not doing a good job, okay? So now it turns out that this is actually not just for this case, but it can be shown for more complex case, although still very simplified. So this was some work done, many, many years ago, where we were trying to understand, again, these applicability conditions in terms of dimensionless numbers. And again, we looked at something that was, very, very simple. A plus B goes to C in the liquid phase, and then this C reacts on the solid boundary. And in this case, also, you can define different Damn-Collar numbers depending on the reaction time scales and diffusive time scales. We also have a Peclet number because we also have advection. But ultimately, what we find is that if you start with your classical system of equations that describe the evolution of concentration of A, B, and C, so the 3 species with appropriate boundary conditions on these solid-liquid interfaces, where only C is reactive with some kind of nonlinear reaction, and then you upscale, so you do this, apply this homogenization theory. What you would get, again, the point is not the equations, but kind of the punchline afterwards. So you would get kind of what you expect, which is like just a system of coupled, nonlinear partial differential equations that have, source terms that represent reaction, We do have the effective coefficients, like I've defined, we discussed before. We have this dispersion coefficient that, again, depends on the closure variable, the same thing before. But now the closure variable, the interesting thing is that this closure variable, what is the boundary value problem that should satisfy, again, through the theory? Well, it's this kind of boundary value problem. The the point is that this boundary value problem can be written in this way, completely decoupled from macroscopic quantities only when appropriate conditions on the order of magnitude of Peclet and Damkohler are satisfied. So if Peclet and Damkohler have certain orders of magnitude, then I can, the closure variable does not depend on macroscopic quantities and I can separate scales. But if these conditions are not satisfied, effectively I cannot separate scales and my closure variable is dependent upon macroscopic quantities. So essentially I cannot separate scales with this model. And ultimately you can even put together these conditions and express them in terms of that separation scale parameters that we had before. So essentially, these conditions put constraints on the temporal scales that are, or the interplay between temporal scales of the physics that actually can be described by that particular type of model. That particular one. So if your physical system has parameters that fall inside this regime that is all colorful, then you can use that upscaled equation, and if it falls outside, you lose predictivity. So you cannot ensure anymore that your prediction satisfies the conditions of the theory. Now, these conditions are only sufficient, but not necessary. So what you know is that if you're inside here, the model has to work. But if you're outside here, you don't know whether the model will work. It might, but it might not, okay? So that's how you get, essentially, from the derivation, kind of the applicability conditions associated to each particular model. When do I stop? I forgot. Thank you. So by then, essentially what we have learned is that homogenization theory and so practically all other upscaling theories, you can show that you can map almost, at least a couple of famous ones onto each other. Not only you can get upscaled models that in this context we call Darcy scale, so my apologies, this is like very much porous media people, but it can do much more than that. So it allows you to determine the applicability conditions of that particular model that you have derived, and it also allows you to self-consistently assess model predictivity. How? Because if I know the applicability conditions, I also know that if the model I derived is correct, then the upscaled model needs to satisfy, needs to match the average of the pore-scale by errors that are not larger than epsilon, which is what is enforced by the theory. So I can do an immediate numerical check the errors. Is it good? Then the model passes. It's not good, then there is an error in the model, and the model needs to be improved. It can do other things that I might be able to touch upon depending on time. It actually helps us to derive also coupling conditions between models at different scales. But this is, we'll see whether we get there. Okay, so now the question is, okay, we did A plus B. A goes to B, and honestly, like I always received this pushback, which was a very legitimate one, which was, okay, you can derive all these things, but nothing looks like A plus B goes to C. Point taken. Yes, very few things looks like A plus B goes to C, probably except A plus B goes to C. So what do we do with it? With this mess, right? Now. Let's take a step back to the thermal runaway problem, where, again, you might think that the equations that we have to upscale are not so complicated. Again, here we have just a conduction equation for the packing material, and here we have a conduction equation for the battery cell, with the addition of a heat generation term that is highly nonlinear. So what this heat generation, so these are generally, this source, one way to think about this is that these are measurements from arc experiments, okay? So what this says is that the battery generally generates a little bit of heat up to a certain temperature, but then after a certain temperature, the battery, undergoes thermal runaway, the heat generation spikes up, and then the battery burns down. Now, even for this very, very simple and apparently innocent system of equations, things get very complicated. Of course, we have boundary conditions, at all these interfaces, which I'm going to skip over. Things get complicated, but before we want to check that model actually at least can predict something very basic, let's say the no ignition and ignition scenario. So that type of system of equations can actually predict both a case where if I burn the cell inside, you have heat propagation, but essentially everything propagates quite diffusively in the system. And the other case is when you ignite the cell, then essentially this ignites all the other cell and essentially you blow up the battery. So that model can capture at least the basic behaviors that we want to distinguish between. But the question is, now, this is expensive, so can we do better? Well, yes, we have the theory. We know that we have those upscaling theory. They allow us theoretically to do everything we want. We can derive the macroscopic equations. We can integrate, topological information in the parameters, and we know how to do it rigorously. So in theory, it's all beautiful. But in practice, it's a mess. It's a mess because this derivation, even for a system that is that simple, they're tedious, time-consuming, prone to error. And then if you want actually to find applicability conditions for different combinations of parameters, operating condition, and you can add to the list, you have to do the upscaling every single time. And it is bad news because this is how bad it is. Like, it is bad. I promise, it is. And this is not even all of it, okay? So it is bad. So then when we didn't even have reactions. Like, we didn't even have reactions. So imagine if you have to pile on like all kinds of reactions because you have oxygen that is being generated. It's just not doable. So that's when we started thinking about we sitting in this kind of quite uncomfortable spot where we realized that in computational physics, there was a lot of advancement being done in disciplinary modeling where disciplinary modeling, I think really our ability to probe experimentally temporal and spatial scales that are always better and finer, and also, in the computer science and numerical methods, GPUs and whatever, quantum, blah, blah, blah. So we are making advancement, but the math, we still do it like Lagrange, like by hand, right? And there is no problem with it. There is really no problem with it. We love it. But the only problem is that when you do math by hand, really complexity becomes a tuning parameter. And so because I was so wounded by that comment, we really didn't want to have complexity as a tuning parameter anymore. And that's when we decided that the goal was to automate. We wanted to automate this framework. And so what we did was to look at symbolic computing and upscaling. I'm gonna be very brief here, but essentially symbolic computation is the science and technology that aims at automating a wide range of processes that are involved in solving problems in mathematical physics. And again, it's very different from numerical computing because it emphasizes discrete and exact computations versus approximate computations as in numerics. And the symbols represent mathematical objects that are subject to predefined rules. Now, of course, symbolic computing is nothing new. It's used very extensively in computer science. For example, if you do logic, right, they use theorem proving kind of formalism. It's used in mathematics, in combinatorics quite a bit. But we were not aware at that time, that was in 2020, that formalism, like those involved in this kind of applied math procedures to coarse-grain, were ever implemented in this type of, or proven could be done in this type of framework. And so the idea was really to say we want to now automate the upscaling procedure. And the reason why we want to do that is because we want to maintain the rigor, but also the complexity at the same time, so that people in engineering are not going to tell us this is useless. So what we did was to develop Symbolica. This is a symbolic software that is developed in the language Mathematica, although it's based on an entirely new algorithm that is much more robust than the functions that oftentimes you find in Mathematica. I'm not going to go into the algorithm. I want to say that symbolic computing, in fact, not only is not new, it's very old. She was the first one to have the first concept of symbolic computation in 1842, Ada Augusta. She was commenting on the Babbage analytical engine, and she wrote a beautiful excerpt, but because of time, I'm going to move forward. So now that, we have this Symbolica, essentially the idea is that what Symbolica does is that it takes in equations at the finer scale. So in this particular case, again, our finer scale is this resolved cell scale with boundary conditions on all interfaces. And then that's it. So essentially it takes this as an input and spits out the effective equations. Not only it spits out the effective equations, the effective parameters, and the closure problems that you need in order to determine the effective parameters once you have identified your topology or structure. Now, before we would have done this, it would have taken us quite a long time, but Symbolica really can do it in seconds. So there is a 10 to the 5 speed up. So Symbolica essentially did my PhD thesis, which is not related to this, in 8 minutes. So it was like an humbling experience, but yeah, it is what it is. So Symbolica is a given structure. Again, I'm going to kind of skip through this. But essentially, what it derives is, the upscaled equations in 62 seconds. Now, is this just a matter of speed? Yes and no. Well, yes, for sure, we like this to have these models fast. But I think the most intriguing part, at least for me, was the fact that Symbolica derived equations that we did not anticipate they would look the way they look. So if I had to, well, now I know how they should look, but if I had to guess what was the model that corresponded to that thermal runaway problem, and I had to kind of intuitively get it, I would have never written these equations. So in that sense, in my opinion, what symbolic deduction does is that eliminates the human bias from our perceived or projected idea of what a certain system at the larger scale should look like. I'm not going to go into the details of all these terms, but I can just note how weird these equations are. Because, again, I remind you that we started just with very innocent conduction equations, like very boring. And what do we get here? We get advective terms. We get emergent terms that cross-correlate with the temperature in the other domain. We get a lot of strange stuff. Now, intuitively, I can tell you that this advective term essentially is the term that allows the continuum scale models to simulate the thermal front when this thing blows up, right? If there was no advective term, you would have just a very nice kind of diffuse, behavior, but this allows you to get that. But there are also, again, other terms. The reason why I think, this point, independently of the speed, I think is valuable, is because now you can see that essentially with these terms, we also have additional parameters. Now, the additional parameters from an engineering perspective represent essentially additional axes of optimization that I didn't think I had, if I were to assume that this maybe would, still behave somehow like a conduction equation. Now, but the counter argument is, but how do you know that this even makes sense? I mean, Symbolica may have produced something that is completely wrong. Fair point. Well, the reason why we know is because we can't, again, the framework is does not have leaky points. You get the model, you know how to calculate the parameters, you know what the error should be, and then you check it numerically. And if the test does not pass, Symbolica produced trash. And so what we did was essentially to perform, extensive, testing on the model. And the way we do it is that we run the full pore-scale simulations. Then we solve the equations that Symbolica derived with the parameters imposed by Symbolica based on the unit cell structure. And then we compare. We compare the average, the moving average of the temperature in both the packing and and the cells with the continuum scale simulations. And again, really, these plots, they look pretty, but we don't care about them. We just look at the errors. So whenever the absolute error between these two solutions is below epsilon, then it means that the model has preserved the theoretical bound, okay? So that's all we look at. So we can, of course, do it more complicated things, like we burn half of the domain, and then we see how it propagates. And again, we only and always check the errors. So, of course, once you use continuum scale models, things go much faster. And this is not even like optimized at all. This is like really brutal, simulation. So this could be going much faster. And I think we even over-resolved, like we use a very, very fine mesh. So it's, the ratio between time scale, between the times can be actually larger. Now, as I mentioned briefly before, every time you change the parameters, or you change the chemistry, or you change the packing, or you change the SOC, anything, you would technically have to do the upscaling again. Because the equations, the continuum scale equations that you obtain are dependent on the dynamics that is imposed by the parameters of the models, because they control the temporal scales of transport processes. But of course, do we care now to do this over and over again for different packing? No, we don't, because we actually don't do it anymore. Symbolica does it. And in fact, the reason why we don't want to do it is because you can see that depending on where you are in the parameter space, the model changes. And every model has the same accuracy, okay? So you truncate at epsilon squared with the maximum error at epsilon. Now, this actually recovers one of the models that are generally used to model thermal runaway, that is the conventional lump capacitance model. But what we find is that this lump capacitance model is actually accurate in a very narrow range of the parameter space. And then you might say, okay, but maybe all the data fall in this. No, they don't. They really don't. So not very wise to use this unless you know that you are in the proper parameter space, or you won't be able to, again, predict, be sure that you're getting a good prediction. Now, computational efficiency, which is the last part. Now, we have done, we can do now the analytical derivation symbolically, it's fast. We can incorporate complexity because we don't care anymore. That's all good. But the problem is that we still need to numerically verify these models. So somebody is actually to take the output for Symbolica and code it in. You might imagine that I almost got a revolution in the lab when the output was like this. Who wants to code this to see whether Symbolica just decided not to do the right thing? Nobody really wants. Well, actually, somebody did, because somebody did do it. So, one of my students actually had, at the time, to calculate the weak formulation of that equation by hand. And you can see all the like green check marks, but if you go and look closely enough there is an error. And he couldn't validate the model because of this, the epsilon that didn't validate. So we said, okay, done with it. Like my lab is gonna essentially become just me, like very soon. And I can do this. So, and so then we said, okay, because we are embracing this, not only we want to generate the model symbolically, we also want to generate the code symbolically. We don't want to do any work anymore. And so we did Numerica. So what does Numerica do? So simply, she takes, these are all women. So she takes the output from Symbolica, which are the upscale PDs, the closure problems, the effective parameters, and then essentially calculates the automated width formulation, does the automated time discretization. Then, of course, we need a language transformation because this is all in mathematics, and we have to write an FEM solver, a finite element solver. This still produces chunks of codes. It doesn't produce the whole code, unfortunately, but, it could be done. So we wanted to do a verification example that, again, now is just a reactive transport because we wanted to have a lot of different reactions, just a ginormous mess, which we knew couldn't do it by hand or numerically, like coding it in. And so what we did was to implement, feed it into Symbolica, get the upscaled equations, get the closure problems. There are 17 scalar fields and 7 vector fields. Do it numerically, and then again, we look at the error for the species, and we are all good. Right now, Symbolica actually took quite some time to get that. So I don't know why. Numerica produced the code in 4 minutes. So we still can really, speed up this process a lot. Now, in the last minute, 45 seconds. So I told you, oh yeah, the applicability conditions, and then I'm very kind of cavalier about, but what happens when, we cannot use continuum scale models. Like it does happen, all the arguments, DFT, not DFT, it's kind of the same thing, right? Again, I don't know that part, but. So then, what do we do when continuum scale models lose accuracy? Well, I can tell you immediately an intuitive example when this happens. So if you have reacting fronts or thermal fronts that are very sharp and are sharper than the length scale of an averaging window, intuitively, you know that if you try to represent a function that goes like this with an average, well, your approximation is not going to be good, right? So this thing happens when you have sharp reacting fronts or very reactive systems, things that blow up, things of that nature. So what we do when those things don't happen is that, and we cannot use this in the entire computational domain, is that we build hybrids. Now, I know that this word maybe is used in a different context among this community, but what we mean by hybrid is that we combine essentially mathematical descriptions or equations of the same physical processes at different scales in the same simulation, okay? So we would have a fine scale model somewhere and then couple it with a continuum scale model somewhere else. By the way, the theory also tells you where to put the boundaries, okay? The theory tells you where to put these boundaries. How these hybrid simulations look like, okay, so this is a fine scale simulation, this is an upscaled simulations, and this is a hybrid simulation. So you see here I'm resolving all the structure, and here I'm coupling it with a continuum. Of course, we need to do I'm going to skip this. So of course, we want to couple it in a way that the error of the coupling, because we introduce error when we couple, is always bounded by the upscaling error, right? So that's what happens oftentimes is that maybe this coupling really needs to happen in certain instance in time. So for example, what you see here is that, there is a discrepancy between the continuum scale, which is the dashed line, and the accurate solution, which is the dotted line, only at early times, for example, and you are above the error threshold that early time, but later on things work out just fine. So what we wanted to do is to do actually adaptive in space and time hybridization strategy with automatic detection. So what does that mean? It means that essentially the system calculates, again, quantities that are consistent with the theories and decides automatically whether, we need to coarse grain or downscale. Okay, so this is a case where we have an expanding domain. And this is a case where we have a shrinking domain because we really don't need to have all this resolution. I think with this, I'm kind of done and over time. Of course. Yeah, so, so we are, really working in this area, but I'm very, very much interested in actually try to understand how to connect to smaller scale. If we could get the reaction rates in our boundary conditions from finer scale simulations and understand how to integrate the theories, that would be just wonderful. Of course, we can do this also for electrochemical transport. There are a lot of opportunities for CNN where we can actually, within this theory, also calculate effective parameters very accurately from the images of structures. I'm not going to go there. And then, essentially, I think that's all of it. So if you have different physics, here goes your favorite multiscale systems. We're also interested in actually automating different math. I think that what this demonstrates is that we can actually automate very complex mathematical derivations that are relevant to physical systems. If we did it for homogenization, we can do it probably for another theory. And with this, the final thoughts, I think for me the most important thing is that symbolic deduction and automation not only speeds up things dramatically, but actually reduces human bias in how we understand complex systems. So we kind of, maybe we'll discover models and physics that, going across scales for complex systems, we wouldn't have anticipated to see or expected. And these are the 3 students that have worked with it, on it. So he's the developer of Symbolica, he's the developer of the numerical adaptive scheme, and she's actually the theorist who developed all the thermal runaway part. So with this, thank you.